Hello, Math 30 to 11 students. Let's begin Lesson 5, Prime Number Theory, Part 2. This time, we're going to focus upon the distribution of primes. How the prime numbers are distributed in the set of positive integers, C+. Here's an example problem. There are infinitely many primes. It is related to the distribution of primes. If the prime numbers are concentrated on first 5,000 numbers, for example, or first 5 billion or whatever, then there cannot be infinitely many primes. The reason there are infinitely many primes is because the prime numbers are all over Z+. So, this is an example problem on the distribution of primes, and quite probably the most basic, the easiest one. So, partly as a review, let's do it again. I know we already did it in section 1, but let's do it again. Suppose that there are only finitely many prime numbers, p1, p2, p3, and so on of the pk, and then define an integer, capital Q, as a product of them all plus 1. Previously in section 1, we defined capital Q as just a product, and then we worked out Q plus 1, and sometimes that's more convenient. We'll see those kind of examples later, but in this particular case, it's going to be more convenient if you just start from the product plus 1. So I'm changing it a little bit from whatever I wrote in section 1. So instead of working out Q plus 1, I'm working out Q itself, because plus 1 is already there. And then let us do this modular arithmetic. This product is congruent to 0 modulo pi. You see, it's divisible by pi. It's pi times all the other things. So if you divide by pi, that disappears and we have remainder 1. So this capital Q is congruent to 1 modulo pi. So pi does not divide this Q. And that applies to all prime numbers, p1 through pk. So no prime number divides this capital Q, and that's a contradiction because back in section 1, in prime factorization lemma, I think, we proved that every integer greater than 1 can be written as a product of primes. But this one cannot be, so it's a contradiction. So our original assumption must be wrong. There should be infinitely many primes. Okay. That's probably the easiest example problem on the distribution of primes. Let's go a half a step further. Not even one step, half a step. Let's prove that there are infinitely many primes of the form 4n plus 3. 4n plus 3, what is so special about this 4n plus 3? Well, if I select an integer, a positive integer, then this integer can be this integer will be congruent to either 0, 1, or 3 modulo 4. So k is 4n plus 0 form, remainder 0, or 4n plus 1, four n plus 2, or finally 4n plus 3. So the remainder is 0, 1, 2, or 3 when we divide this k by 4. So congruent to 0 modulo 4, how many primes are there of this form? There's none, because all these are composite. All these are multiples of 4. Next, how many primes are there of this form, 4n plus 1 form? It turns out there are infinitely many, but we're not ready to prove it yet. Several weeks later, we are going to come back to that, but not just yet. That'll have to wait, and let's go to the next 4n plus 2 form. How many prime numbers are there of this form? There is one, just one. It's an even number, and we have only one even prime, case 2. When n equals 0, then this drops out, and we have 2. That's the only prime number. And then finally, 4n plus 3 form. So here's the distribution of primes. Nothing here, infinitely many there, and exactly 1 here, and infinitely many there. And then as for infinitely many here and there, it turns out the distribution is about the same. Probabilistically, I mean, or, oh, never mind, I'm not going to talk about those measurements, so forget about that, but we can prove all those. But all those will have to wait. For now, we are doing only this blue. There are infinitely many primes of the form 4n plus 3. So did I say we are going just a half a step, not even one step? Yeah, that's why. This is trivial, nothing there. That's trivial. There's only one. And as for green versus blue, we are doing only one of those two. So we are just moving half a step, not even one step. All right. Let's go ahead and prove it. How do we prove it? Let's begin with a similar argument as before. Suppose that there are only finitely many primes of the form 4n plus 3, and name those as p1, p2, p3, and so on. And then define something like this cleverly. There you go. Capital Q is 4n plus 3 form again. You see, all those primes are 4n plus 3 form, so it's just capital Q. Now, this product, what did he do with the product in the previous problem? That part is congruent to the 0 modulo pi. Remember that? For any I. That's what we did, right? Maybe we can apply that. And then this is congruent to 3 modulo any pi. Okay, all right. So this capital Q cannot be, is not divisible by any of those primes. There goes a contradiction, right? So we have a capital Q with no prime factorization. Oh, not so fast. We did not assume all primes of this form. We only assumed there are finitely many primes of the form 4n plus 3. There may be many more primes of this form, green. We have to work that out. So this is a bit harder. Ready? Okay, let's begin with a simple observation. Certainly, this capital Q is not divisible by 2. This is an odd number. Do you see that? 4 times something is an even number, plus 3 is an odd number. So 2 does not divide Q, which is the only prime of the form 4n plus 2. So brown is done. Not divisible by 2. Not divisible by any prime of this form. Next, let's go blue. Q is not divisible by any primes of the form 4n plus 3 either. And that's the same as the previous problem. Yeah, we have product plus 3, and this product is congruent to 0 modulo any pi. Remember? That thing is congruent to 0. So 4 times 0 plus 3, so we have just 3. So the remainder is 3 modulo pi. What does that mean? No pi divides q. Pi does not divide q for any I, 1 through r. So blue is done. Capital Q is not divisible by any primes of the form 4n plus 3. Now, how can you prove that capital Q is not divisible by any prime of 4n plus 1 either? Well, to prove that directly is hard. So let's go back to the prime factorization lemma and use the fact that Q can be decomposed by prime factor. Now, none of those prime factor is either 2 or 4n plus 3 form, so all those prime factors must be of this form, 4n plus 1 form. Make sense? There is a prime factorization, yes, we established in section 1, and then we just proved none of the prime factor is 4n plus 3 form, and then 4n plus 2 form either, so they are all 4n plus 1 form, so the factorization must look like this. Does it make sense to you? So, first prime, second prime, third prime, and so on, the last prime, and then they're all in 4n plus 1 form. Now, instead of working out mod pi, let's work it out modulo 4. Modulo 4, then this is 0. That's 0. All these are 0. So modulo 4, we're just multiplying a bunch of 1s. So capital Q is congruent to 1 modulo 4. Do you agree with this conclusion? Let's go back. Capital Q must have a prime factorization, and the prime factors cannot be any of those 4n plus 3 or 4n plus 2 form. They're all 4n plus 1 form, so we have this kind of form. So congruent module 4 will yield 1. However, from the very construction, we can see capital Q is congruent to 3 modulo 4. 4 is 0, so 4 times this entire thing, that's 0. So Q is congruent to 3, not 1. Which is right, 1 or 3, they're different. There goes a contradiction. Our original assumption must be wrong. Our original assumption that there are finitely many primes of the form 4n plus 3 must be wrong. A bit trickier, but we answer the question regarding a distribution of prime numbers. So modulo 4, we can answer the distribution problem on the problem. We can answer the distribution problem on prime numbers sort of like this. No prime here, modulo 0, and exactly 1 prime here, congruent to 2, modulo 4, they're all modulo 4. And then infinitely many here, green, and infinitely many here, blue. And as for their weight and the probabilistic or any kind of measurement, yeah, they'll have to wait. Okay, so much for 2 examples on the distribution of primes. What do you think? Even the most basic examples were very, very challenging, don't you think? We'll come back and discuss a bit more.